Afternoon, lads. Fairly short topic today, which we'll build on as the lessons go on. And this is looking at the idea of centripetal force. To begin with, we need to consider this slightly unusual situation of someone whirling a mass on a string in a horizontal circle. This could be a mace or something like that. It doesn't matter what it is. What we're going to be saying will apply to all objects in circular motion, just to give you something to visualize around it. So in this case, it's held on by a string. We can say the length of the string is r, which gives us the radius of the circle that it's traveling in. And we can just say that whatever this mass is, it's a general mass m. And what we've got here is a bird's eye view of the same situation. So this mass is moving in the anti-clockwise sense. First thing I need you to do with this problem is we're going to assume that the mass is in uniform circular motion. And remember, that means the uniform part there means that we've got a constant angular velocity, constant omega. This is the assumption. These are the problems we're going to work with at A level. We never look in depth at problems where the angular velocity changes. So this is our bird's eye view. What I'd like you to do is pause the video, and I'm going to put the mass in 1, 2, 3 more different points on that circle, still attached to that string. What I would like you to do at each point is to pause the video and draw an arrow to represent the velocity of this mass at A, B, C, and D. As any time I ask you to draw a vector, I want you to think about its magnitude, whether it's changing, and what its direction's doing. So can you pause the video now and have a go at that, please? So if I start at A and draw our arrow, we'll have an arrow in this situation representing the velocity there, arrow here representing the velocity there, coming down here, and moving along there. What do we notice about that velocity? Well, the velocity has always got to be tangential to the circle it's moving in. And this is the first note we can make for this particular problem, is that in circular motion, velocity is tangential to the circular path. Next question we could ask ourselves is whether the length of those arrows would be changing. For that, I just want to go back to our formula, one of our key formula that we looked at last lesson, which was that V equals R omega. Now, in this case, V is our regular velocity, as shown by these arrows. R is the radius of our path, circular path, and omega is our angular velocity. What we can see here is if R is constant and omega is constant, then our V is going to be constant. So really these arrows should be drawn at the same length at each point. Right, I want you to consider one more part of this problem. Um, I want you to imagine that between A and B here, we've got another point, and the mass is happily going around until this point. We'll call this point X. At this point, the string snaps. Now, what I would like you to do is pause the video and draw a bird's eye view of what would happen to this particle after the string has snapped. Please don't worry about any vertical motion. Just worry about what it would look like from this top-down bird's eye view perspective. Okay, so at point X here, if the string snaps, we'd be in a situation where the velocity is tangential. So the mass would just continue in the path shown by that red line if the string was to snap there. What I'd like us to consider now is why that happens. So we need to go back to Newton's laws of motion. First, let's look at the object when it's moving around in a circle happily. Which law applies? The answer is the second, and the reason is this. So in this case, in all circular motion, we say that the mass is accelerating. The reason why the mass is accelerating is because the direction of the velocity is constantly changing. This is a really important note, and it does come up or has come up in GCSE as well. So in circular motion, the object is accelerating as the direction of the velocity is constantly changing. It's a really important point that just because the magnitude of this velocity is the same at this point, it is still accelerating because its direction is constantly changing between each point. Now, what does Newton's second law tell us more about that situation? That tells us that therefore there must be a resultant force. Now, as it happens, we can label the resultant force on this particle, and the resultant force in this case is always going to be directed towards the centre. Now, this is the force that keeps the object in circular motion. And this leads us on to our first really important definition, probably our last as well. And that's our definition of centripetal force. Now, in this case, the definition can be found from the word. The part of this century means towards the centre, and the petal part means seeking. So what a centripetal force is a centre-seeking force. A force, in other words, directed towards the centre of a circle. So I'll put that here. Force directed towards the centre of a circle or circular path. Really important point here, and you'll see the importance of this later on. We talked about different forces right at the beginning of the mechanics topic. We talked about normal reaction force, we talked about weight, we talked about air resistance, all different types of forces. This centripetal force is not a type of force in itself. So if you're talking about an object moving in a circle, it's got to have a force to provide this centripetal force. In this situation here, what is the centripetal force provided by? Remember, what's holding this mass in is this string. So in this case, we would say that the centripetal force is provided by the tension in the string. So centripetal force is not a type of force on its own, like weight or tension or normal reaction force. It is to describe a category of forces that would act towards a centre point of a circular path. In this case, the centripetal force is provided by tension. So we're still thinking about going back to this thing of the string snapping. We said while the object's in circular motion, the second law applies. The object's accelerating because there is a resultant force towards the centre. If that string snaps, what is going to happen to that centripetal force? The answer is that it will go away. So in this case, we're talking about the centripetal force pulling this object in a circular path. When that goes away, there's no longer a resultant force on that object. And what that means is the object will continue in a straight line in accordance with Newton's first law. So that's important. And that's the reason why this particle, if the string broke, would just move off on a tangent. It's a bit more thinking about this centripetal force now. I'm going to give you a couple of examples of objects in circular motion. So we'll go with a planet in orbit, car on corner, and for the third one, we will go for a roller coaster, and I'm going to say on bottom of loop. So if we're trying to picture that, you've got a loop of a roller coaster and we're at this bottom point there. So what I would like you to do, please, for those three situations, to pause the video now, and I would like you to explain what provides the centripetal force. So if we start by looking at a planet in orbit, what's pulling that planet into that orbit, keeping that planet in orbit? This is going to be the gravitational attraction between the planet and the star. So in the Earth-Sun case, it would be the gravitational force between the Earth and the Sun. What about the car on the corner? As the car moves around the corner, it's taking a part of a circular path. What's keeping that car in that circular path? It's the friction between the tyre and the road. Finally then, with the roller coaster, what's providing the centripetal force, the center-seeking force here when the roller coaster is at the bottom of the loop? What it's going to be is the normal reaction force from the track. Those are just 3 examples, and we will develop those examples later on when we start doing some problem solving with this. The last point that I want to discuss in this video is what the magnitude of this centripetal force is. So we've looked at the direction, we've talked about the direction. The direction is always towards the center, and that's what causes this acceleration towards the center. I'm hoping to do some videos to show you where the derivations of these formulas come from, but for now I just want to show you them. There are 2 formulas, and they are equivalent for the magnitude of the centripetal force, and that is F equals mv squared over r. In this case, v is our linear velocity, m is the mass of particle in circular motion, and r is the radius of the path. What we can do with that formula, helpfully, is we can use our v equals r omega formula, rearrange and substitute in for omega, and what we end up with is F equals m r omega squared. These 2 formulas are equivalent. It just depends on whether you're working in terms of the linear velocity, or in this case, the angular velocity. When we look at more problem solving next week, we'll see that there are differences in terms of when we apply these formula. You can always use both, but sometimes you make life a little bit harder by choosing one rather than the other. So those are the formulas which give the magnitude of the centripetal force. So just to recap on that, we looked at this example and we took a bird's eye view and said, how is the velocity behaving? We said, well, the velocity is always changing because the direction is changing, even though the magnitude is constant. And the reason why that velocity is changing is because it's accelerating. Because it's accelerating, there must be a resultant force. In the case of circular motion, we call that resultant force a centripetal force because it's directed towards the center. And we looked at examples of what can provide the centripetal force because it's not a type of force in itself, it just describes forces that act towards the center of a circular object. And we saw that the equation for the centripetal force can be given by either of these 2 formulae.